Hello, I'm Dr. Charles Knight, and this is an installment in my 10 Lectures on Ecosystem Ecology series for my class, Bio 446 at Cal Poly in San Luis Obispo. I'm part of the Bailey College of Science and Mathematics and the Department of Biological Sciences. And this particular presentation, I'm trying to mirror how I'd like students to do a similar presentation, so I'm going to put some instructions about how to do these presentations in here too. But otherwise, it deals with this paper titled The Effects of 21st Century Climate, Land Use, and Disturbances on Ecosystem Carbon Balance in California. It was published in Global Change Biology in 2019. Fairly old paper, comparatively. I mean, anyway, fairly old, but students have to do 2024 or more recent. But this paper, again, came up in my search because I was searching, I think, on net ecosystem productivity and global change biology and California, and the topic seemed pretty interesting, and they have some nice figures. So I'll first talk about my take-home points for this paper. The main take-home point is that drought and El Nino, that is higher precipitation, significantly affect carbon storage in Californian landscapes. So we're going to see that in several different ways in this paper, and they're going to use that information to model how carbon storage will change in California across the next 100 years about. The industrial sources of CO2 are relatively constant through this period, but actually are predicted to decline. Their data from their California Air Resources Board shows a slight decrease, so that's at least a little bit of good news here. But then my third take-home point is that increased temperatures and associated changes in landscape cover, largely trees, combined with fires and land use transformation by humans, agricultural, either removing orchards or changing land in agricultural uses, are all predicted to decrease ecosystem carbon storage in California through 2100. So California, in some wet years, can be a sink for carbon, but most of the time it's predicted over the next 80 years or so, California will be a net source of carbon. So that's, well, at least the carbon stocks are going to decline, and we'll see that model prediction soon. So these are the authors of the paper. There's a bunch of authors, and I'd like to highlight 3 of them. I should maybe have highlighted 4 or maybe some other ones, but my students know that what I try to do is make ecosystem ecology seem like a group of peers, a small group of people that they should start to get to know who's doing what, especially those people working in California. For those that want to stay in California. So the 3 people I'm going to talk about here is Benjamin Sleeter, Tamara Wilson, the first and the last author, and then Paul Selmounts, because I have a personal connection with Paul Selmounts. So Tamara Wilson has a BS degree or Bachelor of Arts degrees in Environmental Studies from California State University East Bay, so a Cal State colleague. That's in Hayward, California, and she got that in 1997, and then got a master's degree at the University of Arizona in 2002. Notably, she doesn't have a PhD, so I think that's interesting for students in this class. Right now, she's a research geographer, a deputy director of the Climate Adaptation Science Centers as part of the United States Geologic Service, USGS. And she uses land change modeling to explore landscape change impacts on regional environmental processes and resources availability, with potential benefits of nature-based solutions. So she's got interesting CV, sort of, and she's kind of a director within the USGS system. Seems maybe to playing a lot of administrative roles, but who knows? Doing a lot of interesting science. Benjamin Sleeter, this is the best picture I could find of him at his son's t-ball game. I think he's the coach of the team, but he also only has a master's degree in geography from Cal State East Bay, so we've got more Cal State connections here. Notably that he doesn't have a PhD, also interesting for my students. I'm not denigrating that at all. It's just interesting for the students to know that you can get to this higher level USGS position as a he's a supervisory research geographer in the Western Geographic Science Center, and his activities focus on characterizing changes in land use and disturbance and how they impact ecosystem carbon dynamics, and this is the topic of today's paper. And lastly, Paul Selmont's got a Bachelor of Science degree from Miami University of Ohio in 1996, and then a master's degree in botany from the University of Wyoming, and that's where we crossed paths, I believe, at least at some scientific meetings at some point, and then a PhD in forest science from Northern Arizona University. And he's now a research ecologist with the Western Geographic Science Center at Moffett Field in California, also with the USGS, and his research seeks to quantify how terrestrial ecosystems respond to drought and land management practices at regional to continental scales. So all of these investigators are synergistic in studying these large-scale dynamics, and a bunch of them are geographers. So what I do in these presentations is I read the abstract, and that can seem in a presentation to kind of really slow things down. But you know, the scientists spent a lot of time thinking about the words that go into this abstract, and I think it's a good grounding for any presentation. And so I don't need to improvise and make anything different. They already said these long sentences, and so we're just going to take the time to read the abstract. I'll read the title and then the abstract. Try to read it fairly slowly too. Effects of 21st century climate, land use, and disturbances on ecosystem carbon balance in California. Terrestrial ecosystems are an important sink for atmospheric carbon dioxide, or CO2, sequestering 30% of annual anthropogenic emissions and slowing the rise of atmospheric CO2. However, the future direction and magnitude of the land sink is highly uncertain. We examined how historical and projected changes in climate, land use, and ecosystem disturbances affect the carbon balance of terrestrial ecosystems in California over the period 2001 to 2100. We modeled 32 unique scenarios spanning 4 land use and 2 radiative forcing scenarios as simulated by 4 global climate models. Between 2001 and 2015, carbon storage in California's terrestrial ecosystems declined by 188.4 teragrams of carbon, with a mean annual flux ranging from a source at negative 89.8 teragrams per year to a sink of 60.1 teragrams per year. The large variability in the magnitude of the state's carbon source sink was primarily attributable to interannual variability in weather and climate, which affected the rate of carbon uptake in vegetation and the rate of ecosystem respiration. Under nearly all future scenarios, carbon storage in terrestrial ecosystems was projected to decline, with an average loss of 9.4%, a decline in 432 teragrams carbon by the year 2100 from current stocks. However, uncertainty in the magnitude of carbon loss was high, with individual scenario projections ranging from negative 916.2 to 121.2 teragrams of carbon, and was largely driven by differences in future climate conditions projected by climate models. Moving from a high to a low radiative forcing scenario reduced net ecosystem carbon loss by 21%, and when combined with reductions in land use change, i.e. moving from a high to a low land use scenario, net carbon losses were reduced by 55% on average. However, reconciling large uncertainties associated with the effect of increasing atmospheric CO2 is needed to better constrain models used to establish baseline conditions from which ecosystem-based climate mitigation strategies can be evaluated. So many of the authors on this paper are geographers, and so not surprisingly they have a really nice GIS map of California and different land use cover classes GIS, just remember that's Geographic Information Systems. And this is a very detailed pixelated map, which this was produced back in 2019. They're probably even better now, but you can see almost every pixel of California is classified as some type of land use. So I really like this map. It makes sense, they're geographers, and then they're applying their geographic skills to form a model of carbon change and carbon stock change, or carbon storage change over the next 100 or 80 years. So they use a lot of modeling, and this is a typical ecosystem model, box and arrows. The boxes represent pools of carbon, the arrows represent fluxes, and really this model is too complex to get into in this presentation. Remember my mantra that all models are either too simple or too complex. They're sometimes useful, but usually a little bit wrong in some way or another. But people are doing their best to model carbon dynamics using models like this. Again, it's too detailed to go into the details right here. Their goal is to predict carbon stocks through 2100, and they use 16 years of observational data to train their models like this. This is an example of a model, but they use different climate scenarios and different tweaks of this model, different land use scenarios, to come up with different projections. So these are the 16 years of training data. I'm going to take a look at several elements of this graph. It's very complicated, very, very complicated. So I'm going to dissect different parts of this graph in several slides. So I'll just give you a second to look at it and try to get your bearing. The x-axis is the time step, and these are observational data that they fed into the model. So they have ground truthing data, or basically training the model based on observed data. And teragrams of carbon is on the y-axis here. You got 3 lines that are annual fluxes, and notice it starts at 0 to 750 teragrams of carbon, and then it even goes negative. So if it goes negative, then that's a carbon sink. If the line is positive, it's a source. So not surprisingly, the inventoried emissions are a carbon source, always. But notice they're slightly declining. I have a slide on that. The ecosystem carbon sink is either positive or negative, and we'll see some changes in that. And then we see the total in the triangles. Overall, the California is a source of carbon. Let's just face it. It's a source of carbon even in years when the ecosystem is storing a lot of carbon because of industrial emissions. But let me try to dissect this graph a little bit for you. So these are the inventoried emissions, and I just drew a line on every bar that shows those are the inventoried emissions, and they're declining slightly, so that's a little bit of good news. But again, remember that even in those wet years when the ecosystem was a net carbon sink, the inventoried emissions in those years led to California being a source of carbon, not surprisingly. So the ecosystem carbon storage is either positive or negative. If I circle the ecosystem carbon storage in like large magnitude years, you see that it goes up and down, and I just kind of retrace the line there. So some years are a source of carbon, the ecosystem is, and some years are a sink of carbon. So it's a sink in wet years. So I'm circling the wet years here. These are El Nino years. Exceptionally high precipitation leads to the landscape or the ecosystems being a carbon sink. But the ecosystem is a carbon source in dry years. Conversely, in drought years, which are highlighted here, the ecosystem is a source of carbon. There's more respiration coming off the landscape. And this goes along with the results from the previous paper by, I can't remember his name right now, but the last paper we did. So this is their model again, and the model predicts that decreasing precipitation or drier years and increasing temperatures will lead to carbon stocks declining over the next 100 years. Again, not important to know the details of this model, but this is the output. This is the petagrams of carbon per year storage in California, and these are the stocks. So this is just all the carbon in California, and what we see is a decline through time from 2000 to 2100. There's a decline. The black line is a decline in carbon stocks, and that's largely driven by decreased precipitation or drier years and increased temperatures, and it'll lead to a decreased carbon stock over the next 100 years in general. That's a synopsis of a larger model that was on the previous slide. So I'm back to my take-home points. Drought and El Nino, increased precipitation that is, are significantly affect carbon storage in California landscapes. Industrial sources of CO2 are relatively constant but predicted to decline slightly over the next 100 years, and increased temperatures, associated changes in landscape cover, that is tree cover, combined with fires and land use transformation are predicted to decrease ecosystem carbon storage in California through 2100. So thanks a lot.